Hey, welcome back. We're looking at our second video here on the standard normal distribution. We're looking at standardization and unpacking this idea a bit further. We are going to actually directly address our question from the last video where we had two different maths exams at perhaps different places with different groups, different averages. However, it's similar sort of tests in the same subject. So how do we compare them? And we can't just go by the score alone, of course. So let's do that. We are looking at what's called the standard normal distribution. Now, a few points here to note. The variable is not capital X, it's Z. Okay, so Z denotes the standard normal distribution variable. The random variable for a standard normal distribution is a Z, okay? And the standard normal distribution immediately tells us that the mean is always 0. That's important. And just as important, the standard deviation is always 1. So Z indicates how many standard deviations the corresponding X value is away from the mean. Okay, so it does correspond with an X value. We were talking about transformations and conversions in the previous video, and that's where they're coming from. Okay, so to calculate the Z value, we got to look at the difference between it and the X value, whether it's above or below. Okay, and that is given by X minus mu. And we need to find out how many standard deviations fit into this. We simply divide by the standard deviation. And it's called a Z-score, okay, very important. And there's your formula for Z-score. Make sure you note that, okay. Z is X minus mu over sigma. All right, you're going to use that a lot. So thus the graph of the probability density function for the standard normal distribution, and you might remember from the previous video that was the formula for it, okay, is like this. Okay, it's a standard graph, and along the this horizontal axis we have standard deviations. All right, so we have standard deviations is the increment along there. Okay, and you can see that its mean is at 0. Okay, and as we said, the standard deviation equals 1. So who did better out of the student 1 and student 2? So what we do is we actually find their Z-score. So let's call the Z-score for student 1 Z sub 1. And they got 92. So we've got X minus mu over sigma. And their score, their raw score was 92. The mean for that group was 80. And the standard deviation is 6, so that's a Z-score of 2. Whereas with student 2, we'll call that Z-score 2 or Z2, they achieved 88, they obtained 88, and the mean was 78. Standard deviation is 10. So we have 10 over 10, which is a Z-score of 1. Now, both students are clearly above average, okay, 92 versus 80, 88 versus 78. But by how much, and how much can we say in a standardized way? Well, we can look at this student here is at 2 standard deviations above the mean, and this one is at 1. So on the graph, you're looking at for student 1 up here, and they've only got a fairly small number of students ahead of them. Okay, in the next video we're going to talk about the percentages that relate to that. Whereas student 2, above average, but there's a greater proportion ahead of them. So student 1 has done better. We'll see in a future video that the student 1 has only 2.5% of the students ahead of them, and the other student, number 2, has 16% of students ahead of them. Now we're going to do a few examples where we can apply this idea, and it's very useful. And we're going to use this is a tech active part. We're going to use our technology here to do these calculations, a TI Inspire calculator. And here's the task. I'm going to calculate the values of the following probabilities correct to 4 decimal place. Notice that in part A, we're looking at z-scores, okay? And looking ahead in part B, we're not looking at z-scores, all right? We're looking at the normal random variable x, okay? So that's a normal distribution in part B and a standardized normal distribution in part A. So be careful there. All right, so we have the probability that a value z is less than 2.5. So what we're looking at, if we look here, we can see a little dotted line, red dotted line. That's where we're looking at it. We're looking at the probability that a score lies in here, which is quite high because there's a large proportion of the curve less than 2.5. Okay, and because it's continuous, it doesn't matter whether it's equal to 2.5 or less than, it's the same thing because any individual value has a probability of 0 from our previous work. Now, most of the data is within, just about all of the data, I think it's 99.7% of the data is within plus or minus 3 standard deviations. And this one is up at 2.5, so it's going to be pretty high proportion. The probability is going to be quite high, and you can see by the shading that we've got a large proportion of the curve there, a large part of the area. So this is what we do. We enter it in the graphics calculator. So probability that z is less than 2.5 is what we write, and we're going to use what's called, you might want to note this to justify your work, using normal CDF on a graphics calculator, justifying your work. And you can see that I've already done these questions anyway, but you can see them there. But how do you get, it's this first one here, how do you get that? You go menu, statistics, and then you go distributions, and then you go normal CDF, cumulative, okay? And because I'm using a non-cas, I can't put in negative infinity here, but you can see I'll put a very major player in the negative numbers there. Negative 9 to the times 10 to the power 999. Very, very long way into the negatives. Up to 2.5, and it's a z-score, so remember the mean is 0 and the standard deviation is 1. And then voila, we get 0.9938 to rounded. So, rounded to 4 decimal places, 0.9938. Next question is the probability that score lies between negative 1.5 and 1.5 inclusive. So we're looking at z-scores again. We're going to look at using the graphics calculator again, but slight difference here. So we go, again, we go menu, statistics, we go distributions, we go normal CDF, and we are going from negative 1.25 up to 1.25, and it's a z-score again, and we get 0.7887, so that's the answer to that one. Okay, last part. We're not looking at z-scores, as I said. Now we need to take, in the previous video I introduced this notation, that's the mean, and that's, now remember that's the variance, so the mean would be the square root, so the standard deviation is 3. Okay, so notice how the mean is not 0 and the standard deviation is not 1. That should cue into what you've got before. Probability that x is greater than 27. Okay, now we go again to normal CDF, and probability that x is greater than 27 means we start at 27. And we go up to 9 times 10 to the 999, which is infinity essentially. And we had 25 and 3 as our mean and standard deviation. And we get entry error there, 0.2525. Now if we want to convert that back to x back to a z-score there based on this value here, we can do the following. So remember, z equals x minus mu over sigma, and we've got 27 minus 25 over 3. That's 2/3. So the equivalent z-score would be 2/3 or 0.6 recurring. So just goes to show you that z-scores don't have to be integers, like that example with the 2 students doing the exam. Okay, it can be any suitable real value. Positive and negative, in other words, and decimal and integer.